Good morning, everybody, and let's get started on the practical exercises. So today we are going to finish the two practical exercises. So let's see. The first one is the uh, third practical exercise: binary shift key signal generation with noise, and you can find the both introduction guidance from the authors. And so firstly, we can uh, finish the third practical exercise, and there are several tasks we need to do. And in this work, uh, we need to generate a binary shift key signal. Not only the binary shift key, but also the amplitude shift key and the phase shift key signal with noise and without noise. And so let's say the first one is we need to choose some random sequence of the 1 or 0 binary symbols and display these symbols. This signal as the first subplot, and here there are multiple parameters needed for our generation signal, and including the symbol duration, carrier frequency, and your specified the binary data vector, and we need some length of the binary data vector, and the signal noise ratio. Here we have the initial value and 100 decimal. And firstly, we can start to fill this uh, default parameters, and we move to the octave and write the code. So we can write code, and each time we can clear all the variables. And so the first parameter is the symbol duration, and it's 1 second. E equal to 1, which is and the next one is the carrier frequency, and here we use the 10 hertz. F0 equal to the carrier frequency. And the next one, we need our binary data vector, and in here we can it can be the arbitrary sequence of the 0 and 1, and for the data numbers, and we can choose the 10 or more if you want it. So let me random specify some use the like 0 0 1 1 0 1. So here I specify the 10 data symbols. We can also get 10 data bits to be transmitted. Next one is we need to know the length of the binary data vector, and here we have the 10 data bits, so the length is 10. There is n is And the last one is the single to noise ratio. And here we use the initial value is the 100 decimal. So after this work, we can start with first subtask is we need to display the binary data and use the stars function. And here we need to show the all complete the last symbol. Here we need specific with the uh, end of the binary data vector. So it start from the from my case is 0, and the last one will be the 1. So we need to use this part and to show complete the uh, uh, data symbol and display the and we can uh, calculate figure 1. So the first figure, and we use the subplot. So for the first figure, we will arrange the uh, three subplots. So we start we call it this one is 1 3 1 1, and here we need to use the stars steers uh, steers function to display all data. And it start from the 0. And so the x-axis will be the start from 0, and the step is the t, which means the step is 1, and in my case is 1. And for the last part is uh, the n multiplied with the t, so which will be the 10. And for the y axis is we need to show the all uh, data bits, and it start from 0 to the end of the 1. And we can optimize it as add some more information like to let it uh, let the x y relation to be the number, then the 0 and the 1. And we can example labor for the x and the y. So x is and with the unit is second. The y label binary data, and we click on to show it. So right to save this one will be the third practical for the VA. Yeah, it shows the all shows the all binary data, and it start from the 0 to the 10, and we can see here for the 0 for the first symbol is 0, and the second is 0, 0, 0, 1, 1, 0, 1, 0, 0, 1, 1. So it's correct. And we move to the guidelines. So next step is we need to generate the carrier symbol for the one symbol duration, and we need to specify the time intervals. And here we can see it starts from 0 to the t minus delta t, and the step the delta t is the t divided by the 200, and it's the number of the carrier single samples per symbol. And here has more introduction about this part, and we need to plot the obtained signal. We need to uh, match the all symbol, so we need to multiply it with the n, which is the number of the symbols, and here we have 10 symbols, so we need in my case we need to multiply with the 10. So let's get started. And here we use the sign function to generate carrier symbol, generate the carrier signal. So let's this part will be the this work will work for the second task where we need to generate a binary amplitude shift key signal without noise, and we need to display this signal as the second subplot. So second task put binary amplitude shift key signal without noise. So first one we need to uh, do the here we need to calculate the time step delta t. We can name it dt with the time the symbol duration divided by the 200, and it will be the sample carrier signal with the sample time. Time t divided by, and our time interval for one symbol, it will start from the 0 to t minus delta t. So the t will be the 0, and its step is the dt, and is the dt, and this will be the time interval 1. And now we can generate the carrier signal as 0t. As 0 will be the sine 2 pi multiply the frequency and the time interval. This will be the carrier. Carrier signal fragment. Now we can generate the first one. Now we can go on the next steps. The third step, we can generate the binary amplitude shift key signal and use the chronic multiplication. And here is an example how does the chronic function working. And you will see we have a b2 vector and use a multiplied with b in chronic function, and each of them will each of the element will multiply all elements in the B vector, and we can get the 1, 1, 1, 2, 2, 2, 3, 3, 4, 4, 4, like this. So we use the so here in our case, our A is the binary data, and our B is the carrier signal. So we can use chronic function. And binary data is the carrier signal. And here we have to specify with the here for the time interval for the one symbol. We have 10 symbol, and it need to show in the all what is it? In all after the binary amplitude shift key signal. So we need to multiply it with the n. And we can see it as the T with amplitude shift key is, and the Windows specified is that still will be the DD. And for the last symbol will be multiplied with the n. Minus the previously. So it will be the time intervals for the n symbols. And for we can plot the generated binary amplitude shift key signal, and we just copy it and no upload with 3, 1, 2, and here we use the plot function with the T binary shift key and S binary shift key. We agree down. And for the labor. And the label, Y label will be the will be the binary amplitude shift key signal. So let's write. There is a mistake. Let's see. Smudged. We have I-22. Space 312 with the chair. Factor length will be matched. Oh, here mistake with wing to multiplied with a t minus dt. So I specify the time with n multiplied dt, so there is wrong. Let's write again. And it should generate binary amplitude shift key signal. And we can see for the zero data is the after the modulation is also be the zero. So if it is one data after modulation, we can see it can generate some after the modulation to generate with the amplitude, frequency, harmonic signal, and we can see it amplitude is 1. So, and this is the binary amplitude shift key signal without noise. And, okay, we can move to the, can go further to the next step. And for the first the 3 tasks, we will use the add some noise, use the adaptive white Gaussian noise. And here you can see we cannot use the AVGN function, and we need to use the here we can use we need to add noise by ourselves, and we can generate noise by use the function rand, and it can generate random numbers with Gaussian distribution. And we need to use the 2 values, which is the mean and standard deviation. So, and here for the signal, we can see we already know the carrier signal, and the carrier signal is to get the energy. It's quite easy to get because the energy of the carrier signal is just to the carrier signal it multiply itself to just the square power of itself. And the first step we can get this one, and next step we can calculate the carrier carrier signal energy divided by the noise power, and we know the signal noise ratio. Then we can calculate this part, and after that we can calculate the noise power. Then we can calculate the power density sigma. So this is the idea. And after variance calculate, and when we get this one, we can multiply it with the random normal processor because we have the n symbols here, and each of symbol it has the we have the 20 carrier signal samples per symbol, so we must multiply it with them together. So this is the idea, and we can do it now. So first step, we need to generate noise. And for the energy of the carrier, so first we can do this one, energy of the carrier signal, which will be the EB. And we just sum it with the its so this will be the energy of the bit. Next, we can calculate this function, EB divided by the N0. Will be the 10 is the single noise ratio. We already have some initial single to noise ratio. It will 100. So this is the linear single noise ratio. And we can next step we can calculate this one and the noise power. Is EB. Zero. So this one is not power. Mistake here is spectral power density. So next we can calculate the standard deviation of the noise, which is the sigma. Use this function squared and see squared and divide by 2. Standard and we can mark it as deviation of the noise. And for the noise, we need to multiply it with the random function, and for the all symbols in the deviation function will be the sigma multiplied with the stuff, and multiply the and So it finished the noise, and according to the uh, received the signal, we just plus the noise. That's enough. So the modulated signal will add the noise. Is the signal. So it will be the BXK. We rename it BXK noise, and it can use the signal BXK plus. And the time intervals for the here for the n symbols we don't change it, just to use it. And now we can upload it. 3 1 T beta. So this will be the BXK signal with noise. That's right. And you will see here, we can see here, with the noise and without noise, they have the same, right? Because our initial signal noise ratio is initial value is quite big. Let's decrease it like 30. And you will see here, after the 30, it's at a lot of noise here, but it also can be recognized. You will see clear. Uh, Even the zero signal has a noise, but it cannot reach to the highest amplitude 1. And for the 1 data, it after the noise, we can still recognize it can reach to the amplitude of the modulated the signal still has a 1 amplitude. So it's good. Let's decrease it again with the 10. After 10, you can see. So the modulated signal with the noise, we can know nothing, and all of them bad. So it means we need to have some correlative uh, receiver to detect the signal. Even this kind of the bad signal noise ratio saturation. But now we still need to finish the another two modulation type phase, uh, which is the you can see here. We need to do the for other modulation types for the frequency shift key and the phase shift key modulation type. So let's just save it, copy it. Frequency shift key. value 3. So this one is frequency. So we modified it based on the binary amplitude shift gain. And what else? So we need to modification, because in the frequency shift key we have two different carrier frequency, f1 and f2, and which must calculate based on the orthogonality conditions. So we need to have the k value and divide by the 2t, and we got the delta f. Then we can get the different frequency f1 and f2, and we also need to specify the two carrier signals s1 and s2, and after the generate the binary frequency shift key signal with the, we can assume it as the sum of the two binary amplitude shift key signal. And here we need to chronic multiplication both of them and sum of them. And here we need to inverse the binary data vector because it used in the so it means the 1 inverse to the 0 and the 0 inverse to the 1. It shows in the here in this schematic design. Here we use the inverse element here. So let's get to it. And firstly, we need to calculate the f1 and f2 frequency. So we just change here back to the 100 initial signal noise ratio, and we can here now we after the first display of binary data will not it won't change the anything. So we calculate f1 and here firstly we need to substitute the k, and the k must be the integer number, so we can start from the k, like anything you want, like 2. Let's we'll talk about what k will in fact impact on the plot. And for the delta f, we can do it df with k divided by ratio. So the f1 will be f multiplied with f like 2, and f2 will be the so this will be the frequency shift gain. And here we need to have the two carrier signal, which is the f1 and F2. Carry single with the two with a different frequency, F1 and F2. And we can generate the binary frequency shift key signal, use the chronic, and we need to generate both. Use the 2 times chronic multiplication and be the 1 and the 2 with the S1, and we need to inverse it binary data with the S2. So here has the, let's see, and for T time intervals with the, sorry, do one more step with the, we need to plus them together with the this. And for the time intervals, nothing changed more, and we can do to show frequency. And it will be the, so we can write. So you will see here, we use the frequency shift key, and it has different frequency, but it shows has the different phase, and we need to change it. So here the K is influence on the showing, and let's change it like 10. And you will see here the K influence on the different frequency, and it's more obvious. It has for the 0 has the more high frequency, and for the 1 data it has the lower frequency, but it still has some, you will see here, has some phase, like for the different frequency has the different phase. So the K will influence on the phase, and we can try more different K to how can we optimize it at like 12. So And here you will see after we specified the k as the 12, and it shows the frequency will quite good, and mostly close them together with the smoothie harmonic signals here, and it also has a different frequency and no very obviously the phase difference. So here I recommend you use the k as the 12. This parameter will influence on the uh, uh, phase, and we hope to the it has the different frequency, and we hope it keep the same phase. So this is the idea. And the next step, we will generate the noise. And here noise will not change the anything because noise is randomly generated, so it not influence on the modulated signal, and we need just the uh, uh, put use the modulated signal frequency shift key signal plus to the noise, and here we can see we just change it here with the frequency signal. Just change it. Noise we don't need to change it here. Change the label. That's right. 50 S0 undefined. Oh, here. Yes, we need to use the S1 because we specified the S1. And for the S1 and S2, their energy power they are same because in the lecture part we already mentioned about the E1 will equal to E2 and equal to the E. So we use the one. Any one of them, they will be the same. And you will see this is the binary data. This is the frequency shift key modulated data. This is the binary shift key with the noise data. And we here the single noise ratio is the 100. Let's decrease it. Will look how do it will look 30. So after the 30, and we can see some noise added in the modulated signal, but we still can recognize the which part is the 0, which part is 1. It's still very apparent. Now we can decrease it again, like 50. And all of them get messy. Nothing can be recognized. So it shows after modulated the signal, we cannot uh, learn which part is binary data, which part is 0 data, which part is 1 data, the data symbols. So, and let's move to the third. Let's move to the third modulation tab is the phase frequency shift key. And for the phase shift key, we can use we just need to convert the binary data to the non-retained 0 before we use the chronic multiplication. So because this already introduced in the lecture. And for the binary phase shift key method, we just convert is to the 1 0 to the 1 is convert to the -1, 0 convert to the +1. This is the idea. And we just close it and with rename it. BPSK. And here we change back to the 100 initial single noise ratio, and for the BPSK here. And before the chronic multiplication, we need to convert some to the NRZ. So we have the SB and we have the data bits. Now we can convert it to the NRZ. How to say? This is also the 9 modulated method. We just use the let's see. We just use the -2 multiplied with the binary data +1. Then it can get our wanted signal with the 1 convert to the -1, 0 convert to the +1. And it will be the -2 multiplied with the binary data. And we need to generate the frequency. Shift key. Frequency shift key. So noise part, we don't need to change anything, and will be 0. And we'll for the here we just change here and see noise and ESK. So everything changed. That's right. And here we can see this is the binary data. This is modulated data. Oh, there is some mistake because here is the Z with here chronic we have yeah, here. Now everything should be correct. Let's share. Yes. So we can see it has the different frequency. It has different phase, right? Like 100 phase difference here. This is for the non-noise, no noise added. And here we add noise. We have same with the different phase. this is initial case with the 100. Let's decrease it at 30. But we'll go on. And you will see the modulated signal plus the noise. It still has some very obviously difference of its the phase. Yeah. Here we can also see the phase. So 30 will be quite a good value, and for you we can still decrease it at like 50. Let's go on. Yes, for the 15, nothing can be recognized. So for the third practical work, and you will analyze the you will repeat all of the modulation steps and make on your conclusions on the noise immunity of this modulation type, like different trial with different signal ratio. And so this is for the third practical exercise, and let's take a break, and we will continue at 11. Okay, so thank you, and let's start at 11 o'clock.
Goodbye.